Okay, welcome. Thank you very much for coming. My name is Warski. I work at Software Mill. I'm the CTO over there. I do a lot of open source, some mentoring. And it's not my first time at GeeCON. Actually, I'm not sure how many times I've been here, but thanks for the organizers for accepting me once again. They took the risk. And yeah, let's start. So we'll be talking about effects. We'll try to define what an effect is. We'll try to look at various effect systems out there and their various characteristics to try to answer the question, is it worth using an effect system or not? But before that, let's actually try to define the problem in a bit more general way. So here you can see a function and the same function with some types added. And I think over the years, we've discovered once and again that static typing is usually beneficial. Maybe not in scripts or something like that, but once you have some larger piece of software, static types usually gives us some value. So if we take a step back from static typing and look at what do we do actually by adding static types, we are adding some structure to our code, right? We are adding some constraints for ourselves. So we can no longer write any text as code. We also have to kind of satisfy the compiler, right? So we sacrifice some of our freedom, some of our flexibility in order to get some benefits from the static typing, right? So we are adding some structure which constrains us, but in many cases, and at least in the case of static typing, this constraining is usually beneficial. So we will see if we can extend that a bit further. And static types have a lot of benefits, which many languages have discovered, right? So we've repeated this learning process over and over again, even in languages like JavaScript, which now have types as well in TypeScript. Python has types now as well. So I think it's quite safe to say that static typing has kind of won, at least as far as larger pieces of software are concerned. And static types are beneficial for a number of reasons, right? You might like them solely for documentation purposes. It's easier to read the code. It's easier to explore the code. You might get some IDE completions. You might refactor with more confidence because the compiler will actually verify for you that the refactoring was successful, at least in some degree. You get compile time verification that the code you wrote actually makes at least a little bit of sense. It might also be a great tool for reviewing, especially now when we will see more AI-generated code. Maybe static types will be actually beneficial here as well, because on one hand, maybe the AI will be able to talk with the compiler and automatically fix any compiler errors that it introduces. But if we try to review code, and I guess at least until AI generates straight assembly, there will be a stage where we will be reviewing the code generated by a machine. It actually might be easier to review something that has static types. So this might be beneficial as well. Static types also eliminate whole classes of bugs, right? These are usually simple bugs, but still it would be something that we would need to test and we would need to fix ourselves. And here we get that out of the box. So we don't have to write those tests, which is always good, even if, or rather, especially if they are quite stupid or simple tests. In some cases, from static types, we can generate code, such as type classes in languages such as Haskell or Scala, or through implicits. We can get some compile time optimization, so there's quite a lot of benefits as well. There are some disadvantages, but we will conveniently skip them, as they don't fit, the bigger picture. Anyway, what's the problem we are trying to solve? So can we extend these benefits we get from static typing? Can we extend these benefits we get from adding some structure to our code to effects, right? And if we do that, will the benefits still outweigh the costs? Because these constraints always have some costs, right? We may add so many constraints that it's not possible to code anymore in a sane way. So that's probably going too far. Like if we try to, we can go to the coq, for example, style of programming where you prove that the program actually does something that you want to do, but it's very hard to write the program. So that's probably going too far. Anyway, before we do that, let's try to define what's a side effect so that we are on the same page. So if we go to Wikipedia, there's a definition. It reads that a function has a side effect if it has an observable effect other than returning a value to the caller. And that's okay-ish, except that it's kind of recursive because we say that a function has a side effect if it has an observable effect. So now you might wonder what's an observable effect. So I will try to come up with a better definition than Wikipedia. It happens. So we will say that a function has a side effect if, apart from returning a value, which is like the main purpose of any function in a programming language, it also changes some observable behavior of the system. So what is important here is that we only are concerned with observable behavior. So probably each function, side effecting or not, it probably changes some, I don't know, registers in the CPU, right? But you cannot observe it from your programming language unless you are programming in assembly. So if you are doing Java, you can't see that the registers have changed. So we are only concerned with observable behavior. And this behavior is also probably contextual. So there are some side effects which we are definitely not concerned about, right? So one example here might be memory allocations. Calling a function might probably exhaust the memory and cause an out-of-memory exception to be thrown. But it's probably not something that we want to track. If you do, you probably should use Rust or something like that. In Java, we are usually not interested in actually tracking if a function has the side effect of allocating too much memory. That would be quite outside the scope of the language. Another example of contextual effects might be logging. Logging is rarely an interesting effect to track, so it's just for debugging purposes, usually for tracing. Observability in general. So again, logging might be an example of an effect which you don't really want to track. As a side note, we often talk about side effects. The name side effects comes from medicine. It's something that happens to you when you take some medication and then something happens that shouldn't happen. I don't know, you want to cure your cold, you get some drug and, I don't know, your skin turns blue. That's a side effect, right? And they are usually unwanted and undesirable. While when we have a function which has side effects, we usually call that function because it has these effects, right? So we will talk simply about effects. I don't think side effects is the precise terminology here because we often call these affecting functions because they have effects, not because they have some unwanted and undesirable behavior. This unwanted behavior would be a bug, which we would have to fix. So we will just talk about effects. So what are some examples of effects, right? So the prime example would be exceptions. If a function throws an exception, it actually never returns a value to the caller, right? So quite clearly, it has an impact on the behavior of the calling method, other than just other than returning a value. And the sole fact that we call a function which throws an exception already changes the behavior of the calling method, right? Maybe it goes to the exception handler, maybe the method exits completely and propagates, pops the stack until it reaches the next exception handler and so on. So that's an example of an effect. And by extension, I/O, which might always throw exceptions, is an example of an effect, but also because I/O usually changes something in the world, right? It might update some state. We might call some REST endpoint, which changes something in the state. So, and this might impact the behavior of the system further on. Similarly, writing a global variable is an effect because we change the outside world. However, interestingly, reading a global variable is not an effect, right? Because if we only read, we don't change anything outside of the function that we are in. So reading a global variable, not an effect. Writing, yes. Starting a thread might or might not be an effect, depending if the thread is started and fully encapsulated within the function. It's started and stopped as part of the function invocation. That's probably not an effect, right? It's just an implementation detail of the function. If starting a thread, on the other hand, might throw an exception, then yes, we are dealing with an effect. And another side note, we often talk about functions which are effect-free or pure, and these are distinct things. So a function is effect-free if it doesn't have any effects, right? So it doesn't modify the outside world in any observable way. And a pure function is something more. It's effect-free, and it's also idempotent, meaning that we can call it again and again, and we'll always get the same result. So a pure function, for example, can't read a global variable, right? And it's a mathematical function then. So these are also distinct terms. Okay, now we know what an effect is. Let's go to effect systems. So again, we can go to Wikipedia and read the definition, which is quite formal, starting with formal systems that describe effects of programs. But I like the definition from Unison. Unison is a functional programming language that we will talk a bit more later. In Unison, the definition goes as this, is that an effect system are guardrails for expressing the program's logic involving effects. So this kind of is similar to the constraints that we've been talking about, right? So it somehow guides you in how you can write your program when the effects are present, right? So effects such as I/O, effects such as exceptions, and so on. So it aims to help you in writing these programs, to make it easier, to make it more understandable, and so on. And speaking of, why would we want an effect system? So we would need some motivating example to actually explore the different options that are out there. So as a motivating example, let's look at an RPC call. RPC, remote procedure call. So we want to invoke some method on another machine, right? It might be over HTTP, it might be over any other means, SOAP, or whatever you like best. So there is some temptation to make these RPC calls look and behave the same as a local call, right? So you might want to, write a nice library, a nice framework where a local method call looks and behaves exactly the same as a remote procedure call, and it's indistinguishable from the outside. It's tempting, but these two types of invocations are fundamentally different. They have different latency, for example, right? In a remote procedure call, the latency is more or less random. Oh, you have to treat it as random. You never know how long it will take. With a local call, it's much more predictable. But the biggest problem is that the two types of invocations have different failure modes. So with a remote procedure call, you might get intermittent failures, right? It might work one time, and the second time you call it, it doesn't work, and then it works again. You might get timeouts because of network, because of other things. You might get partial failures where you actually make the call and it succeeds, but you never get the reply. So if you don't get a reply, well, maybe the call succeeded, maybe not, you don't know. And that's something that's very different from a local call, right? If it succeeds, it succeeds. Otherwise, you can repeat it, for example. So these two types of calls are very different. So maybe it actually makes sense to somehow separate them. And for our programming language, for our library, framework, whatever we use, to somehow distinguish between those two types of invocations. Trying to emulate this synchronous method dispatch over the network is an invitation for bugs to creep in, so we will try to eliminate this class of bugs as well. And this is closely related to a distributed systems fallacy. The first one, that the network is reliable, right? The network is not reliable, we can get all sorts of behaviors. So when discussing why we would want an effect system, there's a couple of areas that we might want to cover, right? First of all, you might just want to know that a certain function or method has some effects. It might be for documentation purposes, it might be for reading, code readability purposes, it might be, again, for the purpose of reviewing code that's generated by AI. or maybe you are just curious and you want to have this separated. But there's more to these systems that they might give you. I guess the most common use case is that an effect system allows you to manage failure modes. We've talked about I/O failure modes, right, when we have a network, and that's also closely connected to resource safety. When you allocate a resource, a database connection, or open a file, you actually want to make sure that it is closed when you don't need it, or in case of any errors. When you have multiple resources, you want all of them to be closed in the right order, and so on. So these effect systems might actually help you to ensure and to guarantee that these resources are handled properly. They might also give you even more power in refactoring. In some approaches, you can represent an effectful computation as a value, and this allows you to use normal refactoring in your IDEs to reorganize your code. We will see this more closely later. Effect systems also often provide you a custom runtime, which might make it possible or easier to work with asynchronous computations. Until Loom, we had to somehow build upon the synchronous Java runtime, which only exposed platform threads, and we had to build on top of that to provide an asynchronous runtime, which actually allows you to use the system resources in a more effective way. So that's also what these effect systems do. They might also have other features such as tools for concurrency, tools for providing dependencies, which might make it easier to test your code by substituting the dependencies which actually use these effects. Okay, so how are we going to implement an effect system? Well, the answer, I think, among all of the effect systems out there is quite simple. We are going to extend the type system in some way, and various languages allow you to do it in various degrees. So Java allows some extensions are built in. Kotlin is probably more flexible here. Scala is even more flexible. So you might achieve different results depending on what kind of flexibility the base language gives you. Sometimes the effect systems are built into the language. Sometimes they can be built on top. So we will evaluate a couple of these effect systems, and we will look at the number of characteristics that they have. So we will look at failure management, for example. How do they allow you to manage failures? What kind of guarantees they give you? We will look at the syntax overhead, which is quite an important factor, in fact. How much they influence the way you write code. Is it still readable after you actually use the effect system? This is connected with control structures, so can we use control structures such as ifs, fors, while, and so on, which we know from our base languages when using these effect systems. We'll also look at things like concurrency and tooling, which I've mentioned, type safety, so how type safe is the effect system, does it provide a custom runtime? Referential transparency is connected to being able to treat effectful computations as values, and thanks to that extract them as values and manipulate without worrying about the ordering of effects. Okay, so let's start our overview of effect systems. If you would have any questions, that's where you can ask them, and I will try to answer at the end. So let's start with the first one. Let's start with checked exceptions, which is the effect system that's built into Java. So we have a piece of code here. It's written in a mix of Java and Scala, so it's a language that doesn't exist, but it's quite short, so it fits on a slide. So the def is a method definition, and the method go home, and then we can see the declaration of the exceptions that it might throw, right? So that's the effects that our method might have. It might throw an IO exception or a wrong fuel exception. And let's see what the method does. So first of all, we fetch the passengers list, probably from a database or something like that. Then we prepare the launch parameters, right? So we give the list of passengers and the heading, and we get some parameters. And then if the parameters have calculated that our goal is far away, we attach some booster rockets. Then we try to fuel up those booster rockets in parallel. So we take an executor, and for each stage, we submit a new task to the executor to actually fuel up that stage. And then we await until each stage is fueled up using .get, and then we launch. Right? Okay, so it's not a very complicated method with some effects. So let's look at our characteristics over here. How does this effect system actually behave? So location precision, what does it mean? Location precision is, can you actually see from the code where the side effects happen? So we can see that we can get an IO exception or a wrong fuel exception, but we cannot really see from the body of the method where the effectful computations are, right? So we don't know which part of the code actually throws the IO exception. So we know that some effects happen, but we don't really know where. So that's why the location precision is low here. We can try commenting out the IO exception and seeing where the compiler will fail. That will tell us which piece of code here is effectful. But yeah, that would need some additional actions. The syntax overhead is low. We are just using plain Scala or plain Java, whatever you want to call it. The type safety is high. If we somehow forget a given exception, the compiler will helpfully tell us that it's missing. There's no referential transparency, which we will mention later. There's no concurrency tools that checked exceptions give us. We can use the built-in control structures. As for failure management, that might be an interesting part. Of course, we can use try-catch to manage failures. And finally, but when it comes to resources, it's not so, well, there is a possibility that you actually might introduce a bug in your code. So if you try to open a file, for example, right, which is a resource, you can use try with resources, for example, in Java to ensure that the file or the input stream is actually closed when you finish using it, right? But nothing prevents you from actually opening the input stream outside of try with resources, and just forgetting about it, right? So the compiler won't tell you, hey, you opened a file here, you need to close it. So the resource safety, there is some, but it's not exactly there. As for failure management, we've got try-catch, as I said, but there's also interruptions, which in Java are implemented using exceptions. So, for example, if we have this concurrent fueling up of all the rocket stages, right, and one of them fails, we probably would want to interrupt the other ones because it doesn't make sense to fuel them up if one fails. So there's no failure management at all here in this code, but so we need to use some imagination. So we want to interrupt if we want to run a number of tasks in parallel. If one of them fails, we probably want to interrupt the other ones. In Java, we can do it using thread.interrupt, which causes an interrupt exception to be injected into the thread. But it has quite a lot of its own problems. It might work if you are careful, but you might also, catch using a catch-all exception. You might, by accident, ignore it. And checked exceptions, I think, are especially interesting because if you go and ask a random person on the street about checked exceptions, they will probably tell you that they are a failed feature in Java. That they're a bit feature, it would be much better if Java had only unchecked exceptions. If you try to understand why checked exceptions are bad or why checked exceptions failed, well, there's a very interesting thread on Stack Overflow which gives you a lot of different answers. I have no idea which one of them is correct or if there's a single correct answer. Maybe it's a combination. But I think it's interesting to see why this effect system is considered a failed one. Some of the more common arguments is that you can always catch an exception and just forget about it, right? That's something that I think every one of us has done at some point. Some say that the exceptions are too specific and too fine-grained. It's too easy to create your own checked exception and shoot yourself in the foot. Some say that they increase the coupling between the calling and the called and the calling method, right? Because in some ways, if you throw an exception, you expose the internals, the internal implementation details of the method. And so the caller now must know what happens inside the method that it's calling. So you couple these two together. Some say that checked exceptions aren't in fact exceptions. They are just a syntax sugar for alternate return values. So if you have a method which throws a checked exception, what you in fact say is that this method might return, let's say, an int, or it might return this exception. Right? We get nice syntax for that in Java, but in fact, these are alternate return values. So there's a couple more of these that you might explore, and you can pick your favorite one. Oh, and an important one is actually no polymorphism. That's also quite common, meaning that you cannot define a generic method which accepts, for example, a closure throwing some exception, and it throws the same exception further on. Right? That's especially visible in lambdas. So when using lambdas, for example, we have the runnable, which declares no exceptions being thrown at all, or we have the callable, which declares that any exception can be thrown. And we would like to define anything in between, in fact, and you cannot do it with the lambdas. So that's often, especially when you want to do more kind of functional-oriented programming, that's often an obstacle when using checked exceptions. If we look at the broader perspective here, how can you do error handling in a statically typed language, I think it will turn out that it's kind of a research problem. There's no good way that people have discovered on how to handle errors in a statically typed language. There's a number of approaches, and all of them are bad in some way. So we've got exceptions, the unchecked variant, which are not so type-safe. We have checked exceptions, we have just discussed. We have eithers, so like alternate return values, which again might be a bit cumbersome to work with. We have multiple return values, as in Go, right, where you return always two values, and one of them might be null and the other not. So that's an experiment. I wouldn't say it's a successful one. We can have some types. We can have monads, as we will see. So we have a couple of approaches, and maybe we should use some mix of them. But I don't think there's like a clear guidelines on which approach to use when. So it's kind of a research problem, which the Java failures in checked exceptions just is a manifestation of these problems. Okay, so let's continue our exploration, and let's look at future. Probably you have seen future before. So future so it's exactly the same method, the same logic, but written using futures. So when working with futures, we can no longer sequence to computations using a semicolon visible or not. So you cannot just write two statements, one after another. So to sequence to computations, you have to use flatmap. That's the way of combining two futures into a single future that executes the first one and then executes the second one. That's what we are doing here. So fetch passengers now returns a future. It will return a future of a list of passengers. And so we need to flatmap that to actually get the list of passengers and do something with it. So once we have the passengers, we prepare the launch parameters. Then we define toHelper methods, which define the futures to run, to attach the booster rockets and to fuel them up. So what we do, at the bottom you can see we've got the sequencing run, right? So we first run the attach method. Def is a method, right? So attach method will be run first. The attach method will call the attach booster rockets method, which again returns a future, or it will do nothing. Then we sequence it with fuel up, which will run a number of futures in parallel using future.sequence. So what we do is we take the rocket stages and we map over the list of rocket stages, and for each rocket stage we call the fuel up method, which accepts a rocket stage and returns a future which will be complete once that stage is fueled up. And then we sequence it once again with pressing the big red button. So let's see how future comes up in our evaluation. So here the location precision is quite high. We can see quite precisely which pieces of code are actually effectful, right? Fetch passengers returns a future because we have to use flat map to sequence computations after it. So that's an effectful computation. Prepare lunch is not an effectful computation. It just returns the parameters. It doesn't return a future, right? So we can see that while fetch passengers is effectful, prepare lunch is not. The same about fueling up. It must be effectful because it returns a future. So here the types tell us, the types told us if a method was throwing exceptions or not before as well. But here the types tell us that the method has an effect, but they also force us to actually use that value in a different way. So the location precision is high, however, syntax overhead is high as well, because we can no longer just write fetch passengers, semicolon, attach booster rockets, right? We have to use this flat map, which radically changes the way we write code. We do get type safety. We don't have yet referential transparency, so no changes here. We do have some concurrency tools, as in the future.sequence. We have to use custom control structures. So, for example, we cannot iterate over these rocket stages to actually over these rocket stages to fuel them up. We have to use this future.sequence, which is a custom control structure, which awaits until all of these futures given have been completed. So yeah, we have to use these custom built-in methods to actually for iteration, for example. Again, we get some failure management, quite similar to what we had with checked exceptions. And again, as for resource safety, we do get some resource safety, but we inherit the same problems as before. So we can still open a resource outside of a controlled block, and the compiler won't tell anything. So now we will make a slight change to the code, but the evaluation will change quite radically. So we will now use a functional effect system. Here is IO. So let's do the switch. And if you look at the code, it doesn't change that much, right? But there's more green. So that's, in some ways, it's better. So how does ZIO work here? So ZIO is a lazily evaluated description of a computation, which makes all the difference. So in the future case, the future is something that's already being computed the moment it's constructed. It's a type which will eventually hold a value that's being computed, right? So when we call fetch passengers, that already starts the computation of the passengers, and eventually it will give us the value. So now, with a lazily evaluated computation, what we get is just a description of a computation. When we call fetch passengers, nothing happens. We just get a description, a lazily evaluated block of code, encapsulated in a custom data type, which, when evaluated, will give us the passenger list. So now we operate on these lazily evaluated computations, and we can combine two lazily evaluated computations into a bigger computation description. And we do that again with a flat map. So that's why the code looks very similar, but it actually behaves quite differently. So we build up these computation descriptions, which are bigger and bigger, by flat mapping them and other operations. And of course, in the end, we have to hand over this computation description to an interpreter, which will evaluate our computation and give us the result. Right? So here the computation happened in the moment of invocation, and here we first create a data structure describing the computation, and then we hand it over to an interpreter which actually runs it. So there's, of course, some overhead in creating the description, but we do get some benefits out of it. So you might also notice that we can now use, here we use methods for the attach and fuel, and if we use vals, it would actually influence, it might actually influence when these side effects, when these effects happen. Here we can just use vals. We can define constants because it's just a description. It doesn't do anything. And the logic is the same, right? We fetch the passengers. We define some helper computation descriptions to attach the booster rockets to fuel them up. And then at the bottom, we actually define the big description that will first attach the rockets, then fuel them up, and then actually do the launch. And the characteristics here is quite similar in the beginning, at least to what we've seen before. So the location precision is high. Anything that returns an SIO is effectful, right? The types tell us. The syntax overhead is high as well, because once again, we have to use these flat maps all over, and they are viral, meaning that once you start using SIOs, you have to use them in your entire application, more or less, because you have to compose these computations and so on using flat maps and other operators. We get type safety. And here, the first difference is that we do get referential transparency, meaning that we can extract any effectful block of code into a value, for example, and it won't change the meaning of the program. We can reuse these descriptions over and over again, and it will behave as expected. So we can safely use standard refactoring tools from our IDE to reorganize our program without changing the meaning of the program. That's not true with the future. We're actually starting a future at a different point in time in the program changes its semantics. If we have lazily evaluated functions, if we have lazily evaluated descriptions, it doesn't matter where we create the description. It just matters how we create the final sequencing. We get some concurrency tools, actually quite a lot of them from SIO. We do have to use custom control structures, and we do get really great failure management out of functional effect systems. Resource safety, for example, I think is worth mentioning here. It's a separate data type. And of course, if you want to work with files, you do need to use, for example, a SIO-aware library to work with these effects. But there's no way to actually use them unsafely. Okay, there is a way to use them unsafely, but you have to try really hard. So like the default way is such that you cannot use a resource in an unsafe way. There is a way where there's an attempt to actually somehow decrease the syntax overhead, and that's called SIO direct. So you can see that there's a defer block. So it's a local transformation of code which runs at compile time and tries to translate code written in direct style, so as we would write with checked exceptions, for example, into the flat map version that we have seen before. So here we've got this .run method. For example, fetch passengers.run. Fetch passengers returns a SIO, and we can, if we are within a defer block, we can .run on it to actually extract the result from the inside. And this allows you to write more or less more familiar looking code, let's say, which looks like a sequence of steps. You don't get the same referential transparency, so you don't get the same refactoring benefits, or at least not all of them, as before. You can use some built-in control structures. You cannot use a for loop, for example, but you can use an if. So that's why it's mixed. So you get some mixed benefits and mixed costs. The downside here is that you actually have to understand both how a SIO works. So you need to understand both this approach, and only once you understand how the flat maps more or less work, you can actually try to improve the readability of your code using SIO direct. So I'm not sure if it's the right way, but it's a way. And changing a bit our approach, let's look at a completely different language, how they manage effects, maybe for some inspiration. So Unison, I mentioned already, it's a functional programming language. It's very experimental. It has many interesting features, such as content-addressed code, but they also have abilities. An ability is a property of a function which tells you what kind of effects this function actually has. And we can see here at the top, we have the signature of the function telling us that the go home method might have an I/O, might use, or that it requires, maybe that's better, that it requires an I/O ability. There's also an apostrophe. This apostrophe is important because it says that the result of the go home function will be a lazily evaluated piece of code. So it's a shorthand for a thunk, meaning a function which takes no parameters and just returns a unit. So to manage effects, Unison uses these lazily evaluated code blocks. So in Zio, everything is lazy by default, right? In the future, everything is eager by default. And in Unison, we have a mix. We have eagerly evaluated normal code, and we have lazily evaluated effectful code. But we have to manage this laziness by hand a bit, however the compiler guides us. So for example, we have the first line here, fetch passengers. We already know that it's an effectful method, so it will return a lazily evaluated computation, and we can force it, so we can run this computation using the bang at the beginning. And because we have called a method which requires an I/O ability to being run, we need to actually propagate this ability to our method as well. The rest, I think, reads in a similar way. We have prepare lunch, which is a normal function. We have the attach booster rockets function, which again needs to be forced because it's a lazy evaluated effectful method. So anywhere we see those bangs, you can be sure that there are some effects or some abilities that are being required. And the compiler will more or less tell you what's missing here. And we can, in a similar way, map the stages, the rocket stages, to create a list of lazily evaluated effectful functions. And then for each such function, we create a thread where this function is actually being run. So if we want to evaluate this approach, the location precision here is high because we know where the effects happen. That's where the bangs are. The syntax overhead is medium. We have to use these apostrophes and these bangs. There is type safety. There's some reflection transparency, not full, but if you are careful not to refactor this bang annotated code, you should be safe. There's no failure management or resource safety yet because it's a language under development, so this might improve. But if we look at the top half, which is already there, this looks quite interesting. And finally, the last one we will look at is a prototype. Well, it's an imaginary library which we might get if we try to use Loom and build something on top of Loom, actually, right? So Loom itself provides you an asynchronous runtime, so it doesn't really address anything concerning effects. It just allows you to, it allows you to use the system resource in an effective way without having to use a library or a framework which does it for you. So we no longer need, for example, futures or IOs, as in functional effect systems, to manage asynchronicity. We just need to take care of the other features, such as implementing an effect system to manage failure modes. So here we have an imaginary library in an imaginary language, which is based on Project Loom. The idea here is to use capabilities. So we will use capabilities as defined in a possible future extension of Scala. And these capabilities are kind of tokens. They are implicitly added tokens. And for example, the fetch passengers method over here would declare that it requires an I/O capability, right? Meaning that it needs to be provided with a token to actually be run. And this token is the I/O that you can see at the top over there. So the compiler, because it sees that the enclosing scope actually has this token because it's declared as an I/O, it will insert this token to the fetch passengers invocation for you without you having to actually do it by hand. This also means that the location precision of this approach is quite low because you don't really you can't really see where these tokens are inserted unless you try to comment the token out and see where it breaks. But the syntax overhead is low, right? We can just use normal direct style code. We don't get any referential transparency, and failure management, resource safety, well, it's not there because it's all imaginary. But it might be an interesting area to explore for the future. So summing up, we have like 3 main traits which we would like to have. High location precision, so that we can see where the effects happen, low syntax overhead, and we might also want to get referential transparency. It seems we can't get all 3, so it might be tempting, maybe it's a 2 out of 3 again. But it's not even that. It's sometimes 1 out of 3, right? It seems not possible to have both referential transparency and low syntax overhead, for example. So some of these combinations are possible, but some seem not possible. So in the end, you have to answer for yourself a couple of important questions. For example, how important is the lack of syntax overhead for you, right? Are you fine with representing computations as values, which give you a lot of benefits, but then you have to use, flat maps to actually sequence your computations. So, unfortunately, it's a trade-off. What can you learn from checked exceptions? Why haven't they worked for you, right? What are the problems of this approach that you might want to fix? So before I conclude, just a short mention of my company, Software Mill. We have recently merged into a single group with Virtus Lab. So we have now even a broader range of expertise on board. So if you would ever have a business problem, if you would like to flesh it out in technical terms, we are there for you. If you would have a technical problem, the same. And with that, I would like to thank you. And I guess we'll see if we have any questions. Okay, I can see the questions here. Is Zio an IO monad? Yes, Zio is an IO monad. So I guess that's simple. What do the 3 generic types mean in Zio type signature? Okay, let me find my mouse. And Zio is here. Okay, so the first type parameter, any, these are the dependencies that the computation needs. So this might be, for example, an open database connection needs to be open. It needs to be provided to the computation, or it might be that some scope in which resources are open might need to be provided, an open transaction. So these are like the contextual dependencies that a computation might need. The second type parameter is the error that might be thrown. So that's a bit kind of like checked exceptions, but with polymorphism, because you can write method which transform a Zio computation, whatever the error type might be. And you might also say that a given computation cannot throw any errors by putting nothing instead of exception. And this kind of guarantees you that unless there's a programming bug, at least this computation shouldn't end with an error. And the third type parameter is the return type, here just a unit. But if the computation actually does something, it might be an int or whatever it computes. Okay? Yes. Okay, why is location precision so important? It might not be, of course, that's a good question. But I think since we are dealing with a system which is supposed to tell us where effects happen, we might actually want to see where they happen when we read the code, right? If we want to use an effect system for code readability, if you can't really tell, maybe this will be a better example. If you can't really tell where the effects happen, reading the method, maybe they are not that useful.
But you said that in ZIO, it refers a representation of what you want to execute. But when you read the code, it doesn't look any different. It doesn't allow you to know exactly when the effect will happen, right?
Well, okay, so within Zio or with futures, it's the same. Where you use these computations which have effects, you use them differently than computations which don't have effects, right? These are different. So in the exception case, the fetch passengers method and the prepare lunch method, you use them exactly the same, right? The first one throws exception, the other does not. And you use them exactly the same. In Zio, you are forced by the compiler to actually treat them differently because one might fail in an arbitrary way, for example, and the other might not.
Where do you see that change? I mean, that the compiler forces you to do it?
Well, if you just call fetch passengers, you will get a warning from a compiler that you have discarded a value that's non-unit, and you know the compiler will tell you that you are computing a value and just discarding it. So that's probably bad.
That's in Java?
No, that's in Scala. That would be in Scala. Okay, no more questions. If you have any questions, I'm here for the rest of the conference. Thank you very much.